Our second session is also going to be a presentation, not a problem solving session. Uh, so in this session, I'm going to get into the domain of Unit 2, which talks about continuous probability distribution. Continuous probability distribution is another special type of probability distribution. And it is pretty obvious and it is quite uh, uh, I mean, easy to understand that continuous probability distribution is that type of probability distribution of where the sample space is continuous. Okay, sample space is continuous only when it is not discrete. Or you can say, in other words, directly that a sample space is continuous when it is uncountably infinite. Okay, so we are going to I'm going to explain how the probability continuous probability distribution looks like and what are the properties of its respective probabilities. Now you already know that the probability distribution associated with a discrete case is called probability mass function. And just like that, we can also name the probability associated with a continuous case by a different name, which is called probability density function. There is no such difference between probability mass function and probability density function. Both of them are probabilities, just like twin brothers. But by their name, we can only say that one is associated to discrete case and another is attached to continuous case. Just like probability mass function, probability density function also satisfies a similar kind of properties. Probability mass functions are always non-negative. Probability density function, if we define it by fx, are also non-negative. Total of the probability mass function values is equal to 1. We write summation px equal to 1. Now, in case of continuity, the total cannot be expressed by using summation sign. Summation sign gets replaced by integration sign. And since the total range is now from minus infinity to plus infinity because it's uncountably infinite, so total probability here, which is denoted by integration minus infinity to plus infinity fx dx, this should be equal to 1. One extra property is present, which goes like that. If you want to calculate the probability that the random variable x lies taking the value small and small, taking the value in between small and small b, it means for us to calculate, to integrate the function fx, the probability function fx, and we have to put the definite integral, we have to consider the definite integral whose domain is from a to b. Okay, so I have set here one simple example. The probability density function of the random variable capital X is given by fx equal to c by root over x, where small x is lying between 0 and 4, and fx is 0 elsewhere. That means it is saying that they have considered the probability functions form and the total domain has been taken into consideration. By elsewhere, it is actually meant that if x takes values lesser than 0 or greater than 1, the probability function's value is 0. We have been asked to calculate c because c here is an abstract quantity, its value is not known. After that, we must find that what is the probability that capital X takes the value lesser than or equal to 1 by 4. Oh, just a minute. Let me check one thing. Yeah, okay. And yeah, fine. And then we have to calculate what is the probability that x takes the value greater than 1. Now you see one thing, that the above probability function is only defined, you can say, within this range from 0 to 4. 0 excluded and 4 excluded. Now, remember one thing, when we talk about continuous probability, when we talk about continuous probability distribution, then there is no difference. If you write that capital X takes value between A and B, if you calculate this probability, then you are actually going to integrate fx like this. Now, if I ask you to calculate the probability this, then also you are going to integrate fx dx. And not only this, it is also going to be the same if we ask you to calculate this probability. And similarly, if we include both the points, the probability will be calculated in the same way. So that means probability of A less than X less than B, it is equal to probability of A less than or equal to X less than B. It is equal to probability of A less than X less than or equal to B. And it is, they are all same when X is continuous. When X is continuous. So we have to first calculate, we have to first find out the value C, the value of C. How can we find it out? We know that the total probability is equal to 1, be it continuous or be it a probability density function or a probability mass function. Total probability is always continuous, always equal to 1. So we have to integrate the probability function fx from minus infinity to plus infinity. It should be equal to 1. Now we can break the integration into three parts. We can consider the integration from minus infinity to 0, then 0 to 4, then 4 to plus infinity. But these two probabilities in these two ranges, that is from minus infinity to 0 and from 4 to infinity, you know the probability function's value is 0. So we have put here 0. And in this range, the probability function's value is given to be C by root X. Now, the rest is very simple. You are going to integrate. You are going to integrate this, and you are going to put the definite you are going to perform the definite integration and put the limits to calculate that C is equal to plus minus 1 by 4. Now, just as before, you can say that all the two possible values obtained for C is one is plus 1 by 4 and another is minus 1 by 4. But since we are working on the we are working in the probability space, so it is pretty obvious that minus 1 by 4 will not be considered. Why? Because if we consider C equal to minus 1 by 4, the probability will be negative, and therefore C is equal to 1 by 4. Now here they have mentioned that the probability they actually considered a probability distribution, and they asked you to calculate C. The scenario could have been that they have given you a probability they have given you a function, and they could have asked you whether this function is a probability distribution. If the question is asked in this way, you are supposed to take the integral integration from minus infinity to plus infinity. If the total probability comes out to be 1, then we can declare that yes, it is a probability distribution. Okay, so the question can be asked in other way around. So we have written the probabilities form because C is not now known. The fx is equal to 1 by 4 root x and this. Now, if you are asked to calculate the probability that capital X, this random variable capital X takes value less than 1 by 4. So that means you are going to integrate the function fx from minus infinity to 1 by 4. Now, 1 by 4 is a real number. It is lying between this number 1 by 4 is actually a number which is lying in the range 0 to 4, isn't it? 1 by 4 is a number which is in the range of 0 to 4. So because in the range of 0 to 4, the probability always takes the form 1 by 4 root x. So for this range also, that is from minus infinity to 1 by 4. Now from minus infinity to 1 by 4, you cannot say anything, but you have to break it again, just as I did in the earlier case. Minus infinity to 1 by 4 can be broken into two halves. One is from minus infinity to 0 and another is from 0 to 1 by 4. Minus infinity to 0 is beyond question because here the probability is 0, but 0 to 1 by 4 false, it is a sub range of the mother range is 0 to 4, and therefore we can put the probability 1 by 4 root over x over here, and thus we can calculate the probability to be 1 by 4. Similarly, probability of x greater than 1 can be calculated, and we have used here the theorem of complementary probability, which goes like that: probability of a complement is equal to 1 minus pa. So probability of x greater than 1 is equal to 1 minus probability of x less than or equal to 1. Now probability of x less than or equal to 1 is nothing but the integration of the function fx from minus infinity to plus infinity, minus infinity to 1. That can again be broken into two halves, two pieces, from minus infinity to 0 and from 0 to 1. Minus infinity to 0, the probability function's value is 0. From 0 to 1, 0 to 1 is also again a sub range of the range 0 to 4. So we can resubstitute the value and we can calculate the probability, which comes out to be half. Okay, so in this way these probabilities have been calculated. And just like the discrete case, in the continuous case also, the distribution function can be defined the following manner. If capital X is continuous random variable and the value of its probability density at small t is equal to f of t, then the function given as, see, we have written the thing in the same way we wrote in the case of probability mass function. The only difference is that here we have used the form integration minus infinity to x ftdt. And the theorem which we wrote after that, according to this theorem, similar to that theorem, we can have another theorem for the continuous probability, for the probability distribution function, probability density function, which goes like this. This particular theorem connects probability density with its distribution function. So it is saying that if fx and capital Fx are the values of the probability density and the distribution function of capital X at small x, then probability that capital X is taking the value between small a and small b is fb minus fa for any real constants a and b, so that a is less than or equal to b, and fx is calculated as the derivative of the function of capital Fx, because capital Fx is the integration of the function fx, so fx is the derivative of the function of capital Fx, provided the derivative exists. Here I have shown you one example where the example is show that the given function is a probability density function. See, I was just telling you, this kind of questions can also be asked. Find the distribution function of the random variable capital X whose probability density is given by this. Okay. Now, if you want to prove that this given function is actually a probability function, then you have to show that the total probability in this case is 1. So you have to integrate fx from -infinity to +infinity. We have broken the region in 4 parts: -infinity to 0, 0 to 1, 1 to 2, and 2 to infinity. In the extreme ends, the probabilities are 0. And in between, probabilities have got 2 different values. One is t and another is 2 minus t. And after integrating, we are getting 1. So the given function is indeed a probability function. And fx, the distribution function, can also be calculated in the following manner. Fx is given by this, and the distribution function is obtained by integrating certain things. Now you see what have I done over here? I think this calculation which is in front of you right now, this calculation doesn't need any explanation. It is quite obvious. Once you have understood the thing like distribution function and probability function in the discrete case, the similar thing is happening in the continuous case. Only thing which you can ask me, that why distribution functions are considered, is because sometimes in certain situations probability functions are not given. Rather than that, distribution functions are given, and we have to study the system by looking into the distribution function. So distribution function is also a kind of probability function. It is nothing different. It is related to the probability function. So sometimes it is not possible for us to calculate the probability functions. Where not becomes somewhat difficult for us to define the function, probability function, be it discrete or continuous. But it may so happen that in that certain situation, the distribution function is easy to obtain. So therefore, in probability theory, both of these set of functions are actually studied. Okay. Now in question number 3, I have introduced one definition actually. And with respect to the definition, I have set one question. The definition goes like that: a random variable is said to be uniform random variable in the interval AB if its set of possible values is this interval and its density curve is a horizontal line as shown in figure. Now what is that? Okay, now look at this figure. The figure is in front of you. The density curve is shown, and it is taking value in between the points A and B. They are asking us to determine the height of this density curve. The density curve is in the form of rectangle. It has bounded a region in the form of a rectangle, and we are going to calculate the probability that capital X takes value lesser than or equal to a plus b by 2. So how this analysis has been done, let us try to find it out. In the analysis part, what I have done is that, as the figure is showing you that the random variable is defined in the range AB, the function as shown in the curve is actually a rectangle with a base and a height. It has bounded a region. Okay, and since the height of the rectangle is not known, so we are assuming that the height to be capital H. Now the area of the rectangle, you know, is given by the formula length into breadth. And since the rectangle, the function is defined within the range AB. Let's see the figure once more. Okay, so the base, this part is definitely b minus a. So base is b minus a. This length is b minus a. And since the curve is a density curve, we know the total area under the curve will be equal to 1. So unit area is being contained by a probability function. If you have an entire area, the unit portion is contained by the probability function. So integration a to b fx dx must be equal to 1. And this integration is nothing but the area of the rectangle, which is b minus a into h, which is equal to 1. So from there you can calculate the height to be 1 by b minus a. Okay, and this why did I write this? I don't. Fa equal to, oh, okay. This is the height 1 by b minus a, which has been calculated. Okay, let's see the figure. You see this, since the shape is uniform, since the shape in the figure's shape is uniform, so the height at the point x equal to a is same as the height at the point x equal to b. That means in rectangle what happens, the breadths are same, na? The breadths are of same length. So therefore you can say that the height, that is 1 by b minus a, is the functional value at the point x equal to a, and or the functional value at the point x equal to b, if you represent that fx is actually giving you the height of the rectangle. Therefore I have written fa equal to a. And what will be the probability of x less than or equal to a plus b by 2? We calculate the probability just like you did, we calculated it earlier. So it will be, the function will be integrated from minus infinity to a plus b by 2. Break the region into halves, minus infinity to a and a to a plus b by 2. Now put the respective values, because you already know how the function is defined, and you get the total probability. You get the probability of this section to be half. From this, you can define another function. You can define another function, random variable, which has the probability density function of the following form. Okay, so if capital X is the random variable whose probability density function is given by fx equal to 1 by b minus a, when x is lying between a and b and 0 elsewhere, then such a continuous random variable is called a continuous uniform distribution. This is another type of probability distribution, but here I am considering it to be, I am showing you the special case of the continuous probability distribution. The first special case is the continuous uniform distribution. Just like I showed you in the earlier classes, that there are two special types of discrete probability distribution. One is binomial and Poisson. Here I'm showing you that there is one special type of continuous probability distribution, which is continuous uniform distribution. Remember that apart from binomial and Poisson, some other type of discrete probability distributions are there. One example is hypergeometric probability distribution, but it's not there in the syllabus, so we don't teach it. Another type of another type of discrete probability distribution is there, which is called Bernoulli distribution, not binomial, just Bernoulli. Another type of discrete probability distribution is there, which I'm going to talk about right now. And I have to mention it because it has some sort of connection with the continuous uniform distribution. Probably you have seen that while defining the current function, probability function, that is fx equal to 1 by b minus a, I am defining it to be a continuous uniform distribution. Why am I writing the word continuous? Because you may ask me that we are studying the continuous probability case, so obviously it will be a why are you specifying the word continuous over here? I could have omitted this word. No, I could have written only uniform distribution, but this has been done because of some special reason, because there is a uniform distribution which is also discrete. Now you can ask me, what is that? What sort of function? How this function looks like? Okay, so the discrete uniform distribution looks like this. Probability of x equal to x, which is equal to 1 by n. Okay, for all x, it is equal to 1 by n. Now, when we learn probability, we actually start with this sort of probability function. For example, when we toss a coin and we say that the coin is unbiased, we say probability of probability of head is 1/2 and probability of tail is 1/2. So that is a kind of discrete uniform distribution. When we toss two coins and we say that both the coins are unbiased, then we put probabilities 1/4 to each of the possible cases, that is HH, HT, TH, and TT. That is another situation which is discrete uniform. So there is a situation which is called discrete uniform, and to distinguish it from the uniform distribution in continuous case, we have used the bracketed term, and we have mentioned specifically that I'm talking about the continuous case. Therefore, I have put the word continuous inside the bracket. Now, in binomial and Poisson distribution, after knowing those distributions, what have we done? We tried to find out the mean of the binomial variate and the mean of the Poisson variate. Okay, here also, after knowing the continuous probability distribution, a special type which is discrete uniform, we have to know what is the mean of the uniform variate and the variance of the uniform variate. So we have calculated the mean and variance. Here I have shown you, but this calculation, actually, it would be nice if I showed you how to calculate the mean and variance of the binomial variate. If I get chance later, I'll show. But here I'm showing this because you may be asked, suppose you do not know what is uniform distribution is, how does it look like? Just consider it to be a function fx, okay, and this function where you are supposed to calculate the expectation of the associated random variable. So here actually I'm showing how to calculate the expectation of the random variable when random variable is continuous. You already know that definition of the expectation, the formula of the expectation remains same. Only thing which changes, it's the summation gets replaced by integration. So here you see we are integrating the quantity x multiplied by fx in the range of -infinity to +infinity. I'm not talking about how the integration have been done. You can do it very well, but after the integration, the expectation of the uniform variable has come out to be a plus b by 2. It is a formula, and you have to keep it in mind. Just like you keep in mind that expectation of binomial variable is np, variance of the binomial variable is npq, expectation of and variance of the Poisson variable is lambda. Just like that, remember that if capital X is a uniform distribution, its expectation is a plus b by 2. A and b are the range inside which the random variable is defined. Expectation of x square, you know, it is calculated by summation x square into fx. Here I'm just integrating it, and we have calculated this form. You don't have to remember this, but try to remember the variance of the uniform random variable, which goes by the formula b minus a whole square by 12. These small questions may be asked in the online examination. Okay. So I have noted down, I have written here this particular definition, the thing which I have calculated in the form of a theorem, that if X is a continuous uniform random variate in the range, then mean is a plus b by 2 and variance is b minus s whole square by 12. And in this particular case, we actually say that capital X follows uniform distribution in the range AB. Here I have shown one example where it is mentioned that X is a uniform distribution in the interval AB, and its mean is 1 and its variance is 4 by 3. It is given. So we are supposed to find the probability X less than or equal to 0. Probability of X less than or less than 0. To calculate the probability, we have to know the range, because otherwise the definite integration cannot be performed. But the range is not given. Only it's given that A and B, this A and B is unknown, and the known things are that its mean is 1 and its variance is 4 by 3. But since we have already calculated the mean of the uniform random variable is a plus b by 2, and variance of the uniform random variable is b minus a whole square by 12. So we are equating a plus b by 2 with 1 and b minus a whole square by 12 with 4 by 3. Now just solve the system. You will get a equal to -1 and b equal to 1/3. And the corresponding function fx is calculated as, now fx form is what? 1 by b minus a. Now b is 3 and a is 1. So 1 by b minus a will be 1 by 3 minus of -1, which is 1 by 4. So we have got our function fx, and the limit -1 and 3 has also been obtained. So we know a and b. You can very easily calculate the probability that x is less than 0. The rest part, that is to calculate probability that x less than or equal to 0, I have, as you can see, that I have already left it for you. Try to calculate the probability by yourself. You have already understood what I mean to say. So this much for today. This much for today's session. I hope you have understood what I actually tried to communicate with you, and I'm moving pretty fast. I'm actually it seems I'm kind of hurry. Okay, so what can I do, because the time is too short. Anyways, you have the book, you have my note, you will have my notes, you have got some of my notes, so you just keep on studying. And you have already seen your marks, which has been uploaded last night in the platform. Now CA1 is over. Just keep in mind that CA2 is coming. Everything will be moving very faster. Okay, so you just don't stop studying, and you keep preparing yourself for the upcoming examinations. With this, I'm going to conclude my today's session. Hope to meet you in the next week. Till then, bye, and I'm stopping the recording.